Swayam Prabha. Digital India. Educated India.
It is a great honor for me to attend the symposium celebrating Professor Satsuyamasi on his 75th birthday. And we have interest in reaction path and dynamics. And today I introduce the expanding the concept of reaction pathways. So under the Born-Oppenheimer approximation, molecular theory is divided and treated by electronic structure theory and potential energy surface shape and reaction dynamics. So chemical reaction can be studied in these three categories. And Kenichi Fukui, he developed the frontier orbital theory. So this is a reaction theory on the basis of electronic structure. And also later, he introduced the mathematical definition of intrinsic reaction coordinate for elemental reaction. This is a definition of reaction path tangent. So by introducing this definition, nowadays we also calculate IRC when we study the reaction mechanism. And once reaction path is determined, we can develop the full dimensional potential surface based on reaction pathway. So along the reaction pathway, one can calculate the potential curvature. Then by applying harmonic approximation, we can get full dimensional surface. Then it is easy to extend it to reaction path Hamiltonian. This was done by Miller, Handy, and Adams. And so in this Hamiltonian, reaction motion, reaction coordinate motion, and vibrational motion are treated separately, but they are coupled through curvature coupling. In this equation, B is the coupling between normal mode coupling and normal mode reaction coordinate coupling. And in the same year, Shigeki Kato and Keiji Morokumar developed and proposed a method to examine which vibrational mode is excited by the reaction path curvature. So in this picture, the curvature induced outward motion due to centrifugal force and leading to vibrational excitation. And another aspect of reaction path based dynamics is the bifurcation. So we published some review on intrinsic reaction coordinate with Professor Maeda and Professor Morokumar. So Morokumar was a person who first calculated IRC for real molecule in 1977. And I have interest in reaction path bifurcation. And Maeda developed the automated reaction path network method. So this leads to the reaction path network concept. So now we replace the single IRC with reaction path network by using this Maeda's method. And also today I introduce two new methods. One is reaction space projector. And in this method, we reduce dimensionality reduction approach to describe the high dimensional reaction path network. And also we project the dynamic trajectory on the same reaction space. And also we focus on electron movement along the IRC. We named it natural reaction orbital. So at the latter part of my talk, I introduce these two methods. So first method, reaction space projector. So this was mainly done by my previous PhD student, Tsutsumi. So in this method, we use classical multidimensional scaling method. So actually, a reaction path defined in 3n or 3n minus 6 high dimensional coordination space. And trajectory also defined in the same space. And by reducing the dimension, and so by using this CMDS approach, we pick up the important coordinate, principal coordinate. And in this case, we choose two most important coordinates. Then reaction path network and trajectory can be mapped on this same figure. The key idea is interstructural distance. So molecule, it's if n-atomic molecule, 3n Cartesian coordinate, and distance of these two different structure can be calculated like this. But we need to define the center of coordinate axis and orientation of coordinate axis. Then we use capture algorithm. Then these two structures are overlapped as much as possible. And the center of mass is used as the origin of coordinate axis. Then we pick up many structures along the reaction pathways, and we measure interstructural distance for each pair. Then by applying CMDS, we define principal coordinate. And later, trajectory data are mapped on this dimension, reduced dimension space. So this is an illustrative example. So this we call RESPA, reaction space projector analysis is applied to this SN2 type reaction. So this reaction was studied by Hase, and they propose non-IRC path concept. So actually, the IRC is not SN2, and this is IRC. So first, fluorine anion tried to escape, but it returned and it is coordinated to OH minus. This is IRC. And black line, the energy variation along the IRC, and red curve indicates reaction path curvature. So reaction path is one-dimension curve in 3n dimensional coordinate space. So, but it is not straight line, it is curved. So we can define reaction path curvature by numerical differentiation of reaction path tangent vector. So there are two regions. Reaction path is curved region. But this reaction coordinate includes all variation of all atoms variations in one dimension. So by applying this RESPA analysis, we can define two coordinates. So reaction path is drawn like this. So reaction path is curved, very largely curved around this region. This region corresponds to B, region B. Region A, not so curved, but this is because the reference structure, the number of reference structures is very small, this region. So reactant, transition state, region A, region B, and product. So from this analysis, we recognize this reaction path is highly curved, this region. Then we consider the dynamics of trajectory. So there are two patterns. So we run 50 trajectories. Number of trajectories is 50. And 20% trajectory proceeds along the IRC. So first trajectory try to escape around this curved region, but it returns due to the attraction force of IRC, and it reaches to product region. But 80% trajectories shows this behavior. So, fluorine atom succeed in escaping from this moiety. So, SN2 reaction occurs. So, from this analysis, people can understand what happened in dynamics based on the reaction path network, reaction pathways. So, next is the reaction path network. So, here, this RESPA analysis is applied to 3 IRC pathway. So, this includes the target is gold 5 cluster, and the minimum is 3 minimum, mean 1, mean 2, means. These 3 correspond to minimum structure on the potential surface. And we include 7 transition state. And VRT is very rich transition. It is related to reaction path bifurcation. So mean 1 is the global minimum. This is C2V symmetry. And the TS11D is connect mean 1 and mean 1. So it means mean 1 consists of 5 identical gold atoms. So gold atom and gold atom are exchanged. This is a kind of reaction. Okay. And starting from TS11D, we run the trajectory like this. So it is difficult to, from this animation, what happens in gold 5 cluster. But on the base of this reaction space, trajectory initially proceed along the IRC, but once it jump to another IRC, and it go around TS13A, but it return to mean 1. So once IRC reaction path network determined, we can do the kinetic simulation on the basis of reaction path network. But actually, in dynamics, reaction path is defined in the same configuration space, and the molecule can jump from one IRC to another IRC in dynamics. And next is the bifurcation. So reaction path bifurcation, it is well-known symmetric case. So this picture is the IRC for mesokishirasuka. And this is the minimum, and transition state keeps CS symmetry. So CS symmetry is conserved along the reaction pathway. So the terminal point is this structure, also transition state. And the hydrogen move in this direction or other direction, and there are 2 minima. So in this case, the Barre feature of IRC changes from Barre to Rich at this point. So this point is called Barre-Rich inflection point. In several reaction systems, this type of IRC was have been reported. But there's another type of bifurcation, asymmetric case. Asymmetric case, so these 2 products mirror image each other. So right hand side and left hand side relation. But asymmetric case, P1 and P2 are totally different type of product. And in this case, the IRC is connected to only one product. So this case, TS is connected to P2. So actually, in dynamics viewpoint, P1 is directly connected from TS. But from IRC analysis, it is not difficult to find this. But now, in many organic chemical reactions, this type of asymmetric bifurcation occurs, people recognize. So I show example. So this is a reaction COH, the phenyl CO CH2 Br plus OH minus. and this transition state, and two possible product. And so OH attack right carbon or left carbon. So then two different products. And in this case, bromo, nylon, leave. So this is a structure. So reactant, transition state, and these two products. And two products are connected by a single transition state. So by changing this X substituent, in some case, IRC is connected to this. And other case, IRC is connected to this. And in the case of X equal H, hydrogen case, IRC is connected to EQ sub. So starting from this transition state, energy is down and it leads to here. Then this product is connected to EQ add through this transition state. And along this IRC, we calculate the vibrational frequency of orthogonal mode. And some point frequency becomes an imaginary number. So this is a Barré-Rich transition point. So asymmetric case we call Barré-Rich transition. Symmetric case Barré-Rich inflection. We distinguish these two concepts. So in this case, people think reaction proceeds in stepwise manner. So once EQ sub produced, then it changed to EQ add. But from the viewpoint of bifurcation, it directly go to EQ add. So around this region, some Barré-Rich transition feature occurs. Another case, this is para CF3 case. IRC is connected to EQ add. So please compare. So this is the case for X equal H, and X equal PCF3, it directly go to here. Okay? Then IRC connected to EQ sub like this. And Barré-Rich transition also occur around this region. So the reaction process is this OH minus is bound to here. In the previous case, OH minus bound here and bromo escape. Then we apply this reaction pathway to analyzed by RESPER. So this is a case for X equal H, and principal coordinate 1 and principal coordinate 2. And this is a case of the second reaction, X equal para CF3. And starting transition state, this around this here, Barré-Rich transition occurs, and then it leads to substructure. And this IRC also calculated. Then we apply RESPER analysis. And in this case, there are two highly curved regions. So this is a transition state, and this is add structure. Okay. So one initial first IRC and the second IRC. But for X equal PCF3 case, starting from transition state, it goes to sub. And then it is connected to ADO. And then it is connected to sub. And then we can merge these two IRC pathway in the reaction space like this. So this picture is provides very intuitive picture for this reaction. Actually, these two are different molecule, But in this analysis, we eliminate the substituent part, and also bromo atom also is eliminated. Then we can plot the multiple IRC pathway of different molecular system in the same reaction space. Then we can imagine. So around here, barrel-rich transition occurs, and some line can be drawn here. So this is a transition state. And this region is a sub-region. This region corresponds to other region. So we can imagine what reaction path bifurcation occurs when substituent change. So actually, we change substituent for many cases and plot in the same figure. So second case, actually, Professor Surihari discussed about Hawk case, and Hawk provides many interesting chemical reaction. And this case, this is also pericyclization reaction, and A and B react, and there are three parts, and 2 of 3 are bonded. So there are 3 different products can be produced. And actually, the reaction IRC is connected from A plus B to C. So TS1 exists between A plus B and C. But there is no direct transition state between A plus B and D, and between A plus B and E. But between C and D and between C and E, we can locate the transition state. So we have 3 transition states. And Hawk also locate 3 IRC pathways, and they did Affiliation MD simulation and get this result. So 93% trajectories lead to C, and very minor trajectories go to D and E directly. Actually, IRC is connected to C, so this is a reasonable result. And we apply our RESPA method to this reaction. Okay, in this case, 3 IRC pathway, and TS1 is mostly A plus B, TS1, and C are connected. And actually, we found there is some shoulder feature. You can see this shoulder. And TS2 and TS3 barrier, the energy region exists around this shoulder region. And actually, by applying RESPA analysis, this is a result. So A plus B, TS1, C. And D and E are located like this, so other side, so not this region. Then now it is easy to understand why the trajectory starting from TS1 mostly reach to C, and very minor trajectories go to D and E. So this is a result of trajectories projected on this reaction space. So our result are almost the same as the Hawk et al., but we plot these 3 reaction paths and trajectories in the same 2-dimensional space, and we provide intuitive picture of the reaction process. Okay, the next is natural reaction orbital. So initially I show the Diels-Alder reaction for butadiene and ethylene and butadiene. And Fukui introduced frontier orbital theory and intrinsic reaction coordinate. So homo-LUMO interaction is important. And this is reactant, transition state, and product. And recently, intrinsic bond orbital analysis was proposed and used. In this method, localized orbitals are used. So actually, homo-LUMO frontier orbital theory is canonical orbital, so molecular orbital delocalized. And chemical reaction process is chemical bond dissociate or generation, formation. So local orbitals are more intuitively understandable orbitals. And in this analysis, in the initial stage and the final stage are compared, and the most changed localized orbitals are picked up. So in this case, 3 orbitals, and this is the animation. So this is the energy. This region, orbital change drastically. So in this case, double bond changed to single bond, and newly bond is formed between ethylene and butadiene, and some single bond changed to double bond. So these 3 bonds are picked up. Now this is one way to understand the electron flow. But our natural reaction orbital focus on the change of orbital. So I explain a little bit about that. So molecular orbital is changed along the reaction pathway. So Ci is molecular orbital coefficient, 0 is for a given geometry. So Dr indicates geometrical slight change. So molecular orbital changes like this, and this is first order, and this molecular orbital change is represented by the mixing of other orbitals, other occupied orbitals, and other virtual orbitals. And occupied orbitals mixing is not so important, but virtual occupied orbital normally they are also they don't mix each other, but intuitively, transition state region, occupied orbital and virtual orbital mixing occurs, and orbital feature changes. So we focus on this UVO. UVO, the physical meaning is the molecular orbital derivative by nuclear coordinate. Occupied virtual orbital mixing occurs due to nuclear coordinate displacement. And by singular value decomposition, we can get orbital pairs like this. So this analysis was done for the transition state of this reaction, ethylene and butadiene. And we get 2 important orbital pairs. The first one is this, and by multiplying this occupied and virtual natural reaction orbital, we get this picture. So this picture indicates electron flow. So this color, electron decrease, and yellow electron increase. So electron move from ethylene double bond region to butadiene single bond region. Now this is a second pair. So in this case, electron flow, electron moves from butadiene double bond region to newly bond region. Okay, and you can see this belongs to some symmetry representation. So A prime and A double prime. So natural reaction orbital must be belong to irreducible representation of point group of the molecule structure. So along the IRC, we analyze. And this case, SRAN, for SRAN, NO2 substituent is introduced. This is butadiene, and butadiene and SRAN reaction, but NO2 is introduced. So symmetry is reduced. Then, at the transition state, red curve indicates the magnitude of singular value. So large singular value indicates the mixing of occupied and virtual orbitals occurs very effectively. So at the transition state, there are two pairs. This is similar to butadiene and SRAN case, but in this case, symmetry is conserved, but in this case, by introducing NO2, symmetry is lost. So these two sets indicates these two sets. The same electron flow is represented by these two sets. And also we see this peak. This region, the reaction does not begin, does not start yet. So here, butadiene symmetry changes. Then within butadiene electron flow like this. Okay. Okay. Then we apply this natural reaction orbital to reaction path bifurcation. So the combination of these two topics. So this is a famous organic reaction, Beckmann rearrangement, and this is a reactant molecule. This molecule has a charge +1. And after transition state, water molecule leaves. Then the product, there are two different products. So this is rearrangement. So this benzene ring moves from carbon to nitrogen. The other is this CH2CN part fragment dissociate. So fragmentation. And by changing substituent X, some X lead to this product, IRC product lead to this product, and other case, IRC leads to fragmentation. So initially, the base case, X equal a hydrogen case. So along the IRC, this is energy profile, and this is the singular value. So there are three parts, electron flow occurs. And at the transition state, CC dash dissociation occurs. And the first peak corresponds to water dissociation. And the third peak corresponds to CN bond formation. These can be understood by this picture. And also, along the IRC, we calculate frequency at imaginary frequency part, reaction path bifurcate. And in the bifurcating normal mode, along the bifurcation normal mode, we applied NRO. And this is the result. So electron flow from benzene ring to CH2N2 part, because this tried to escape, dissociate, and now it is cationic, so it should be neutral. Okay. So this NRO analysis can be applied to along the IRC, but for any geometrical displacement, we can apply it. So bifurcation can be analyzed based on electron flow. Okay, so maybe I don't have time. Almost finished. So today I introduce LESPAR method and NR method, and finally I thank to my colleague, especially Tsumi, developed LESPAR. And Ebisawa, he's also my former student, developed NRO method. And this is current group member. And this is grant. Okay, thank you very much.
Swayam Prabha. Digital India. Educated India.